All right, so we came up with the EBT yesterday. All right, so again, your equation has to be continuous. Same hypothesis, but different conclusion. So it has to be a closed interval, and then F will have both a max and a min value on that interval. All right, so if you're looking at the next page, oh yeah, 20 to life, all of you. Yeah, that's what number 3 will be. All right, so for the first one, you have a continuous function, right? Nice and smooth going from A to B. We have a max here at x equals c and a min here at x equals d. Right now, what do you know the derivative is here? 0, and the derivative here is 0, right? Right, your tangent line right there would be horizontal. Right, good. Okay, so you can have a max or a min. Is that a min? Yeah. So, like take that and just. I'll put it like right here. Like point kind of like right there. Clearly, by the 6 millimeters lower that it is showing. Okay, so you can have a min or a max appear at when the derivative is equal to 0. This other one, right, your max is at, again, when your derivative is equal to 0. And your min is at where? B, which is a what? That's an endpoint, right? All right. So you can have them occur where the derivative is equal to 0 at the endpoints. And again, you can have multiple locations of where your maxes occur or mins. So you can only have one absolute max or one absolute min, but they can occur in multiple locations. Well, the interval is from A to B. And I went out in order after that. Cut me some slack, all right? Please. Okay, so if the hypothesis is not met, either the continuity or the closed interval part, there's no guarantee of the conclusion. However, you still might have a max, min, or both. So if you do not have a continuous function, right, so say, for example, we had like a hole kind of right there, right? So now from A to B, this function is no longer continuous. So what it says is that I'm not guaranteed to have a max or a min. I still might, but we would have to do a little bit more work to kind of figure it out. But if this is continuous, then you definitely have a max and you definitely have a min somewhere. So because it's not continuous, it's telling you that you might not have a max, you might not have a min, but you might though. So you have to do a little bit more checking to make sure you're getting the right thing. For this one, with or without the hole? With the hole. Because it wouldn't be a B because you have points over here that are higher, right? We no longer have a max here because, again, we can't, go to this particular value. If that point was there, then that's where our max would be. All right, so it says determine if your EVT applies from 0 to 2. If so, find the extrema. If not, state why, and then determine if the function still appears to have extrema. Okay, so from 0 to 2, will the EVT apply? No, why not? So it's not continuous at what? Right. Not continuous at x equals 1. So that means that I might not have a max, I might not have a min, but we can still try and figure that out. So do you have a maximum value? No, right? If this was all connected, my max might be right there. But because it's not connected, I can't narrow it down to one specific spot. Do I have a min? What would that be? Right. So you have no max, and you have a min of 0 at x equals 2. Okay, good. That's it. What about B? Will the theorem apply? Why not? Right. It would work for the open interval from 0 to 2, but because we're including the endpoints, and I have a vertical asymptote at 2, and then a hole there at 0, I'm not going to be guaranteed anything. So no, EVT will not apply. It's not continuous on the closed interval. So do you have a max? Sorry, will not apply. So based off of just what you're given, are you going to have a maximum value? No, right? I can't narrow it down to one specific value. So it does not have a max. Does it have a min? No, good. No max, no min. Because I can't narrow it down to one specific value, even though it does kind of go off towards infinity, and infinity is obviously very large, but I can't narrow it down to one specific number. All right, what about C? Right, we have a jump there at x equals 1, so will not apply. Correct. Not continuous at x equals 1. Do I have a max? That would be what? Okay, good. And then you have a min of So we'll do half at x equals 0. Good. No, it has to be. Yes. Yes. Well, that, or you could have a you can have an open interval. So if you were doing it from like, instead of it being closed interval from 0 to 2, you could have, so if they gave you an interval like that, then technically the EVT is not going to apply because it's not closed. And then the last one, continuous closed intervals, right? And then the last one, will it apply? No, not on if it was an open interval, then we'd be good. But that's right. So not continuous on closed brackets from 0 to 2. So again, if I filled that in, I filled that point in, then it would be a continuous function on the closed interval. Then we would be good to go. But because I don't have values there, it would only be an open interval from 0 to 2. So it looks like I still, though, have a max here at maybe a half of 3. You have a max of 3 at x equals a half. And then you have a min of, we'll say a half, negative a half at x equals, yes. We're guesstimating. That's what we're doing. We're guesstimating. Right. Right. Mm-hmm. So the question would be, so that you're saying if the question was like, is this function, do you have an EVT, does the EVT apply on this open brackets from 0 to 2? And all the points were filled in? Good question. Right. I think you would, if that were the case, I feel like you'd have to check the endpoints. Like, so you'd have to make sure that it would be continuous on the closed interval, and then if it's continuous on this, then it's obviously going to be continuous on that. So even though they're only asking for the open interval, you might have to check the closed interval. Right. She's saying if instead of the question was different. They were asking you for the open interval instead. Would the EVT still apply? And I'm not positive, but I think. I don't think so. I don't think so. Mhm. Yeah, that's kind of what she's saying. That's I think you'd have to check the end. So you're saying like something like, I mean, you could still find answers, but I don't feel like they would ask you a question just looking at to open brackets. They might ask you for a closed interval. Today? Average. All right, now most of the time you guys are going to be asked to find extreme values from equations, not really graphs. So how do we? No, it's not useless. All right. Now you have like a graphical way of understanding it. Now you can apply it to an equation. So what different values of x can extreme values occur at? So we have things called a critical value of a function that's in the domain, right? That value is when the derivative is equal to 0 or the derivative does not exist. That point is called a critical value, and the point is called a critical point, okay? So what you want to look for, if you were having an equation, right? Say we had an equation and the graph came out to be looking like that. And they say, okay, find for me the critical points, okay? The critical points are when the derivative doesn't exist or it's equal to 0, okay? So based off of that graph there, where would you have a critical point? So where does it not exist? The derivative, where does it equal 0? Three? Again, they occur at x values. 1/2 would be a critical value, right, because the derivative does not exist. And then this, I guess, is 3/2, or 1/2. That's where your derivative is equal to 0, right? So those 2 points, no. Right, yeah. So if you draw a tangent line right there, it's going to be horizontal. So that tells me that my derivative at that point is 0, right? And then because you have that kind of sharp cusp turn there, that's the derivative does not exist there. Yeah, well, this changes direction too, kind of, right? But the derivative here does not exist. Right here, it would be 0. It's more smooth this way, right? Here? Well, the derivative wouldn't exist there, right? So I guess, yeah, you can consider it like that. Yeah. Not the endpoints, no. They have to occur somewhere in between. Yes. Right. Yeah, so this would be like vertical is, right. Horizontal right would be 0. Correct. So what type of like sharp turns, right? So you got to be on the lookout for like absolute value of x, right? Any absolute value always has a sharp turn. Equations like x to the 2/3, they kind of have a cusp at 0. So you need to be on the lookout for equations that look like that. All right, the next thing it says, absolute or global extrema can only occur at a critical value or at an endpoint. We've already kind of talked about that. So that's, again, where the derivative is equal to 0 or does not exist, or at your endpoints, right? So that would be like either at A or B if you were given a closed interval. All right, so there is another type of extrema. They are called relative or local max and mins. All right. Now you can have many multiple relative and local max or mins. You can only have one absolute max and one absolute min. So I try and think of it as like these guys are all like town mayors. You have many of them. You only have one governor, right? Think of it kind of like that. Say again? Right. Yeah, something like that. Right. So what a local max is? Yeah. Sorry. Yeah, they're like kind of like the highest point. Right. So it says if immediately to the left and immediately to the right there are no y values greater than that particular value, that's a relative or local max. Okay. So all right. So if you have, say, all right. So I got a graph that looks like that, right? So the absolute max would be right here, right? And the min would be right here, right? Now, if I look at this point right here, that point right here is considered a local or relative max, because if you take this point and you look immediately to the left and immediately to the right of it, that's the highest point on that small little section of the graph. Okay, so this point right here would be considered a relative max because it's the highest point on a very small interval. So if you look, this would be the max. This would be the max, or absolute max, right? This is a relative max, right? So it's not the highest of all of them, but it is right immediately to the left and to the right. Right, you can have multiple relatives and just one absolute max and min, yes. Yeah, good, yeah, right here, yeah. I didn't even see that one. Yeah, that's a relative min, good. Because immediately to the left and to the right of it, you have points higher than it, so right. That would be a relative min. I didn't mean to do that, and look at me go. No, you still would, but you can only have one absolute max value. Like you might have an absolute max value of 5 at multiple locations, but you can only have right. Yeah. Yes, they can have you can have a ton of different relative max or mins. Yeah. Cannot be an endpoint. It can only be when the derivative is relative max and mins only occur at critical points, and critical points are only when the derivative is 0 or does not exist. So they can't occur at endpoints. So the only place where you need to look for relative max and mins is on the open interval. You don't have to worry about the endpoints. Now, if you guys, when you take Calc in college, you might have a professor that says something different. But for right now, for what we do, for what College Board says, you do not have to consider a relative max and a min to occur at your endpoints. They only occur in the middle. Yes. No, right now we're just looking mostly at just the derivative. We've been mostly just doing graphs right now, but we'll get to equations where you need to find derivatives. Right. If you had a crazy graph like that, yeah. And again, relative local extrema can only occur at critical values on an open interval, so they cannot occur at endpoints. Cannot occur at endpoints. Yeah, critical values, again, that's when your derivative is 0 or does not exist. So this theorem does not say that there is a relative or local extreme value at every critical value, but rather every critical value is a potential possible location. All right, and again, I'm going to show you a way to kind of test that. Relative and local extrema cannot occur at an endpoint. So again, you can have multiple relative extrema. You can only have one absolute extrema. All right, so identify all critical values, then determine whether local max, local min, or neither occurs at them. Okay, so right here at x equals a, right? Could that be considered a critical value? And why not? An endpoint, right? So the only thing that it could possibly be is a what? Well, it could be an endpoint, but it can't be a relative extrema. Right, this would be your absolute. What is that? That would be it, yeah. They have to be an absolute, right? All right, what's happening here at B? Very good. That's a relative max. So you have a relative max here at x equals B, and I think it's G. G prime of B is what? Right, so you have a critical value right here at x equals B. All right, so B is where one of your critical values is. Now, what's going on at C? Right, so that's also another critical value, and what would I consider that? Relative min, good. So you have a relative min at x equals C, and I do that all the time. G prime of C is DNE. Good. What about D? No, that is.